Alright, so we're going to look at section 3.4 and a little bit of 3.5, which is our triangle angle sum measures and our polygon sum measures. So we're going to start with something that you're probably familiar with, which is the angles in a triangle. So if we're given a general triangle, just angles A, B, and C, what we want to show is that the measure of angle B plus the measure of angle A and C is 180 degrees. So you've used this before, but now we're going to try to look at a proof. And what we're going to use is our parallel lines and transversal to try to get us there. So we have to define another couple angles, D and E, which are going to be adjacent to angle C, and are going to make a linear pair. They're going to form that line M as we go through this. So we're going to be given that M is parallel to N, and we want to prove that A plus B plus C is 180 degrees, and we're going to use a flow proof here to try to make that happen. So I'm going to start with my given, and from that and some looking at the transversal that I have, this transversal here, I know that D and A are congruent, and I know that because they are alternate interior angles. I also know that E and B are going to be congruent because they have the same relationship. They are also alternate interior angles, but not with the same transversal, but with this transversal here. So, I also know that measure of angle D, measure of angle E, and measure of angle C are 180 degrees, and that follows from the fact that they form a straight line, or my angle addition postulate. They make a straight angle. So they're 180 degrees. Well, I'm pretty close. I have three things adding to 180. It's not the right three things. But with a little bit of substitution, I can show that measure of angle A, B, and C equals 180 degrees with some substitution. So we've taken a general triangle and we've proven that the angles are going to be 180 degrees. Alright, this is the theorem that's in our book, Theorem 312, that we just proved it. And this allows us to solve for missing values, missing angles. So if I'm given x 90 degrees and 62, I can set up an equation that they equal 180, and then it's straightforward to solve for x, and I get 28 degrees. Sometimes it's a little more complicated. We have, in this case, three triangles, the two triangles that are adjacent to each other and the one that makes up both of those triangles. But the angle addition theorem still holds. So they add up to 180 degrees, so I use the red triangle and find that x is 74. And then if I figure out that x and y equal 180, I subtract x, and I should get that y is 106, not 86. So there's a mistake on my solution here. So 106. And then I think I carried that mistake through. But we would plug in our values for y and the 19 that we're given to, again, solve for z. And if we wanted to check it, we could look at the large triangle. We could have solved it there by looking at the outer triangle, and that would have given us a similar relationship as we plugged through it. Alright, we also have just classifications of triangles. So an equiangular triangle means all the angles are the same. Acute, all the angles are less than 90 degrees. A right triangle has one angle that's 90 degrees. An obtuse triangle has an angle greater than 90 and less than 180. Equilateral is very similar to equiangular, but in this case the sides are the same, they're congruent. And if you have an equilateral triangle, you also have an equiangular triangle. So these are going to be a biconditional statement. An isosceles triangle has two sides that are the same, and a scalene triangle has no sides that are the same. So if we wanted to classify these triangles by their angles, we have an equilateral triangle for number A, a right isosceles triangle, and then C, I know it's scalene because none of the sides have the same length, and it's obtuse because I'm assuming this is drawn to scale. That angle is larger than 180 degrees. Alright, we can also look at the exterior angles of polygons. So in this case, 1 is an exterior angle, this angle right here. And we have a relationship that says that 1 is going to be the same as the sum of 3 and 2. So we can prove that pretty straightforwardly with looking at what happens with this linear pair here. That's added to 180, and I also know from our angle sum theorem from triangles that all the angles in the triangle are going to add to 180. And with some substitution, we can get that 1 is the same as 3 and 2. We can now use that fact if we want to solve for our measures. So if I have 1 plus, sorry, that's part of the reason why we don't label angles as numbers, as it becomes confusing unless we put our degree sign on. So angle 1 plus 23 degrees is 117 degrees. I solve for angle 1, and angle 1 is 94 degrees. Alright. We could also look at it like I was saying, of 117 plus something has to be 180, and then we also know the angles in the triangle have to be 180 as well. So that would be a 63 degrees, and we could add them up that way to show that there's again going to be 180. Alright, we're also going to look a little bit at the next section, which is classifying polygons. So we have different names for different sides, so that's how we classify a polygon, is the number of sides. A convex polygon has no diagonal, which are points outside the polygon. So you can see in this case, this is a convex polygon. No diagonal, and a diagonal connects vertices, the corners, that aren't adjacent. None of them fall outside of our triangle, of our polygon. Whereas the one below it, the concave, we have this purple one, diagonal, comes outside of the polygon, which isn't as interesting for us mathematically. So what we're really going to study is convex polygons. Concave polygons, we have a problem with these angles that are going to be bigger than 180 degrees in terms of how we deal with that. So for the most part, we don't, and we just look at convex polygons. So just to show you, we have lots of diagonals that we could look at from each point. As we start to draw them, we get many different things that we can look at. Alright, so we're going to try to use a little inductive reasoning here to determine angle sums for other shapes, really looking at interior angles. So I'm going to look at the number of sides, the number of triangles, and there's a reason why I'm going to do that is because we have a theorem that we just proved about the angles in a triangle. So there's a triangle, there's 3 sides, there's 1 triangle. Now I have a quadrilateral, I have 4 sides, and if I was to split it, it's 2 non-overlapping triangles. There's the 2. If I draw a pentagon, I have 3 non-overlapping triangles. If I draw a hexagon, I have 4 non-overlapping triangles. So we want to look at inductively what's happening here. We can see that as the number of sides are going up, the number of triangles are going up by 1 as well. So we would conjecture that a 7-sided figure would have 5 triangles. And what we really want to get to is the sum of the interior angles. So we know that a triangle adds to 180. We just proved it. Well, if I look at my quadrilateral, it's 2 triangles, and each of them add up to 180. So I'm going to get 2 times 180 as my angle sum. For pentagon, I have 3 triangles that each add to 180. And for a hexagon, I have 4 that add to 180. And so I'm looking at my pattern here, and I would conjecture that for a heptagon, I would have 5 times 180. And so finally, we want to look at what's my case where n is the number of sides. So we have to come up with 2 things. We have to come up with a pattern between from getting from the number of sides to the number of triangles, and then how do we get from there to the number of the sum of the interior angles? Well, it's pretty straightforward. You can see that what I'm doing to get from number of sides to triangles is I'm taking away 2 from the number of sides. Looks like n minus 2, and then that number just gets multiplied by 180. So I get 180 times n minus 2 is my general polygon sum. So if I had an 8-sided figure, it'd be 180 times 6. If I had a 12-sided figure, it'd be 180 times 10. We're going to use that fact to solve for shapes down the road. Alright, so this is what we were just talking about. We kind of proved it. We didn't really prove it, but we looked at the reasoning behind it. We also have an exterior angle sum theorem, which says if you add up all the exterior angles in a polygon, you're going to get 360 degrees. You have to get all the way around. If you don't have 360 degrees on your exterior angles, you're not going to make a full complete rotation. You're not going to close your figure. That's something that we'll use, not a ton, but down the road it'll be helpful to us. So let's solve a problem where we look at this. So we have a regular polygon, which means it's both equilateral and equiangular. All the sides are congruent and all its angles are congruent. And I want to find the measures of the interior angle and the exterior angle of a regular octagon. Okay, well, I have my 8 sides, they're all congruent. It also means all my angles are congruent. And if I was to divide it up, I would have 6 non-overlapping triangles. And so my angle sum is 180 times 6 degrees, so 1080. And each of them are the same, so it means that I can just take that number and divide it by 8. If I divide it by 8, I get 135 degrees for the measure of one angle. And now if I wanted to look at an exterior angle, well, that would mean if I was to extend one of these, I'm looking for this angle in here. So if one is 135, this is going to be 180 minus 135, which is 45 degrees. So 45 degrees is going to be the exterior angle. They're all the same because all the interior angles are the same. Alright, and if I wanted to just do an algebraic solution to something where I was given that the sum is 720, I want to find the number of sides, well, I set those two things equal to each other, where I have my general, angle sum, and then I have a given angle sum, and those can equal each other. And so as I go through and solve that, I would find my value of n by dividing by 180 and then adding 2 to everything.